we are going to focus on each of these groups kind of individually. So now we're going to talk about alcohols and ethers. Now, if you remember back to our functional groups, alcohols have a hydroxyl group or an OH on them. Okay, so anything that contains an OH, single bond OH, right, is a hydroxyl group. The ox, right, and the hydro means it's an H and an O, and it can be attached to a carbon really anywhere. It's still considered an alcohol, whether it's on a carbon on the end of a molecule or a carbon in the middle of a molecule. Okay. So remember, R stands for any carbon group. It can be a methyl or an ethyl or so on and so forth. Okay. So there are three types of alcohols. All alcohols are considered either a primary or one with a little not symbol, that means primary, secondary, or tertiary alcohol. And it depends on the carbon that it's attached to. So if the carbon it's attached to is connected to one other carbon, it is a primary alcohol. That means the other two bonds on that carbon are hydrogens. If that carbon is attached to two carbon groups and one hydrogen group, the two carbon groups means it is a secondary alcohol. And tertiary alcohols are when that carbon that has the OH group on it is connected to three other carbon groups. Okay, so it's depending on that carbon. Now, primary, secondary, and tertiary alcohols do react differently, and that's why we're going to differentiate between those three. So before we get into the reactions with alcohols, we are first going to name them. So again, IUPAC nomenclature, so how to name alcohols. So if you remember, we always have a prefix, a base, and a suffix. The suffix for alcohols, so the group is an alcohol, it ends in OL. Makes sense, alcohol that ends in OL. So instead of ane for alkanes, we will be using OL. Okay, now again, you have to number the carbons, but instead of picking the one closest to the most substituents, you are going to pick the one that is closest to the OH or the alcohol. So the goal is to have the lowest number carbon for the alcohol. Okay, so start numbering the carbons closest to the OH group. If it is a cyclo, then that carbon should be carbon number 1, the one that has the OH group. So really, if it's an alcohol we're looking at, I want you to start numbering as close to that OH as you can. But again, you still need to have like your longest chain of carbons. So we're going to do some examples like this. And remember, if it's on a benzene, that is called phenol. Hopefully you can remember that because of the OL, but it's a phenol or a phenol if it is an OH on a benzene, so an aromatic. Okay, so for example, this molecule has 2 carbons, so it should have a base of F, and it has an OH on one of the carbons, or ethane. The end is anol. Okay, so ethanol looks like this. Now I have this one, 1, 2, 3, 4, 5, 6 carbons. Notice I started counting from the side closest to my OH. So this is hexanol, and you have to tell me where that OH is. So it is on the second carbon, so this is 2 hexanol. Now you'll notice on the ethanol, I did not say 1 ethanol, and that's because if it's on the first carbon, we assume it's on the first carbon. So if you don't put a number, we assume it's on the first one. You do not have to write 1 ethanol. So that's just ethanol. This is 2 hexanol. Then this guy is 2 methyl, okay, 2 pentanol. You still have to tell me where the OH is if it's not on the first carbon. Okay, so this 2 here tells me where that ol is, and you put it right before our base name. Okay, so that's naming for alcohols. Now the properties of alcohols. We've talked about mostly alkanes, alkenes, alkynes. Those are all hydrocarbons. They are not very soluble. They are not very polar. Alcohols, however, can be soluble because whenever you have an OH, you can do some hydrogen bonding for intermolecular forces. So alcohols tend to be soluble in water. However, if you start getting higher than 3 carbons, then they're not very soluble because like this molecule here, this is 1, 2, 3, 4, 5. This is hexanol. This big part over here is nonpolar. This is the only part that's polar. So it's really not going to be very soluble, even though it can make some hydrogen bonds because this is mostly nonpolar. Okay, so once you get past 4 carbons, not really going to be soluble. Okay, so onto reactions with alcohols. So when we react alcohols, so something that has an OH on it, we can do a couple different types of reactions. So I'm going to talk about oxidation first. Okay, in oxidation, what we're going to do is we're going to lose or a loss of 2 hydrogens or the gain of an oxygen. Okay, oxidation, gaining an oxygen. All right, so it does depend, the product depends on if it is a primary, a secondary, or a tertiary alcohol. Okay, so if I try to oxidize a primary alcohol, right, what's going to happen is it's going to turn into an aldehyde. So instead of being OH on the end, the oxygen is going to be oxidized to a double bond O, and then I have an aldehyde. So double bond O and then an H. So the oxygen is going to go up here, and then it's just bonded to an H. Okay, so it really would have, if you look at the formula, it would have lost 2 hydrogens and gained, well, we moved that oxygen away. Okay, now it keeps reacting and you end up with a carboxylic acid. So a primary alcohol, it turns into an aldehyde and then a carboxylic acid. So oxidation, we're trying to add as many oxygens as we can, really, to the carbon, but carbon can still only have 4 bonds. So I have this R group, the R group's not going anywhere. The oxygen is going to be turned into a double bond O, and then we're going to have an OH. So I'm adding as many oxygens as possible. It's going to turn into a carboxylic acid. Okay, so oxidation, as many oxygens as possible, which means 2 oxygens, because that's really all you can have. This is still bonded to an R group. If it is a secondary alcohol, so if you have a carbon that has a hydroxide on it, 2 carbon groups and a hydrogen, it is going to try to do the same thing, but it's going to turn into a double bond O first. So instead of just being an oxygen, it's going to turn into a double bond O. Now, since I have carbon groups on both sides of this, I can't actually do anything else. I can't add another hydroxide because it already has 4 bonds. Okay, so a secondary alcohol turns into a ketone. Okay, you can't get rid of those carbon groups. And then a tertiary alcohol won't react because I can't get rid of any of these carbon groups. So I can't make one of these bonds into a double bond. It's impossible. So if I ask what happens, or I want you to draw what happens when an oxidation of a primary, secondary, tertiary alcohol, this is what you're going to get. Primary is going to turn into carboxylic acid. Secondary is going to turn into a ketone, and tertiary will not react. So it depends on what kind of alcohol it is. Okay, ethers on the other hand. So now we're switching over to ethers. Remember, ethers look like the ether bunny. There's an oxygen, which is the face, and 2 R groups, which are like the ears. So there's an oxygen between 2 alkyl or 2 R groups. So carbon something, oxygen, carbon something. Okay, like an alcohol, but it's in the middle. So solubility. Small ones, again, this applies also to alcohols, are soluble because oxygen makes it a little polar, so it can dissolve, but bigger ones are not very soluble. The way that you name these is you name the groups that are on the oxygen. Okay, so this one has an ethyl group on the left and an ethyl group on the right. So this one is called diethyl because it's got 2 ethyls, ether. If it had been a methyl group on one side and an ethyl on the other side, it would be called methyl ethyl ether. So that's all you name it. I'm not going to have you name a bunch of these. Okay. And then under this also umbrella of alcohols and ethers, I have thiols, and that's because they act very similarly, but instead of an oxygen, we're using a sulfur. Now, if you look on the periodic table, right, oxygen and then sulfur is right under it, so sulfur acts very similarly. So a thiol instead of an alcohol is when you have a sulfur atom attached, usually with a hydrogen like the alcohol, so it's like an SH. Sulfur molecules smell terrible. Okay, anytime you've got a sulfur on there, that's a thiol. It looks like this, right? You get an SH on there. They smell really, really awful. This is the thiols in skunk spray. Notice SH. So that's one of their properties, is that sulfur molecules smell terrible. And they work the same way naming wise as alcohols do, except instead of putting enol on the end, you put thiol on the end. So this one is ethanethiol or ethane thiol. Or ethanethiol. Yeah, that's a lot. So ethanethiol would be an ethane with a thiol or an alcohol group. Again, I'm not going to have you do a bunch of those, but they act the same as alcohols would. Okay, so for examples, I'm going to have you identify primary, secondary, tertiary alcohols and then name them. If I were you, I would try this first and then check your answers. Okay, so I'm going to go through each of these, A, B, and C. Okay, so for part A, I'm looking at this carbon. It has 1, 2, 3 carbons attached to the carbon with the oxygen. So this is a tertiary. B would be this carbon has 1, 2 attached to it. Oh, sorry, I'm looking at the carbon with the hydroxide on it. This carbon is the one with the hydroxide on it. This is only bonded to 1 other carbon, so this is a primary. Carbon bonded to the alcohol over here has 1, 2 carbons on it, so it's a secondary. This is the carbon that has an alcohol on it. So it is attached to 1, 2, 3 carbons. This one is tertiary. And this one is where the alcohol is. So this one has 1, 2 carbons attached to it. It is secondary. You don't have to indicate that in the name at all. So in A, on carbon 2, because I have to start numbering, still at the end, like you can't start at this carbon. You have to start on an end, but you want to start at the end closest to hydroxide. So you could have started with any of these. I would be like, this is carbon 2. I have a methyl group. Okay, so I counted mine 1, 2, 3, and then this is my methyl group. Notice I circled the substituents. So this is 2-methyl, 2-propanol. You could have labeled this one a bunch of different ways, but you would still get the same name. On the second carbon, there's a methyl, and on the second carbon is where the all is. So it's propanol because there's 3 carbons total. All right, B is 3-methyl, 1-butanol. Notice I started counting at this carbon because it's the one that's closest to the hydroxide. So the 1 tells me where my all is. Okay, and then on carbon 3 is a methyl. So 1, 2, 3 methyl, 1-butanol. For my substituents, I've got my longest carbon chain looks like this: 1, 2, 3, 4. Remember, all the carbons in a row, as many as you can. So my all is on carbon 2, so it's 2-butanol. And I also have a chlorine group on number 4, so 4-chloro, 2-butanol. This one's a cyclo, so on carbon 1, because that's where the hydroxide is, where the hydroxyl is methyl 1-methyl cyclopropanol, because it's a cycle. Now you do not have to tell me 1-cyclopropanol. You don't have to tell me that the hydroxide is on carbon 1, because carbon 1 in a cyclo is always where your hydroxyl group is. Over here, this has got to be carbon 1 because that's where the hydroxyl is. So this is 3-methyl cyclopentanol. You don't need the 1 here again, because the hydroxide is always on carbon 1 in a cycle.